So a key challenge in weather forecasting is being able to improve predictions 3 to 4 weeks ahead of time beyond the typical 2-week limit of day-to-day weather forecasts. And this is known as the sub-seasonal range. And one of the ways in which we can do this is by considering the belt of westerly winds 10 to 50 kilometers above the Arctic, known as the stratospheric polar vortex. Now, this vortex varies in strength during the winter as it's knocked about by waves moving up from the troposphere below it, which break in the stratosphere like waves breaking on a beach. And in this way, it's sort of a bit like a wobbly spinning top. Now, sometimes the wobbly top falls over completely in what's known as a sudden stratospheric warming, or SSW, and other times there are fewer waves and the top doesn't wobble quite so much and the vortex thus remains very strong. These anomalous events can persist for up to 2 months, and during that time influence the weather that we experience at the surface. But how well can we predict these stratospheric events and why? And how can we diagnose the stratospheric impact on weather and weather predictions? And so the first thing which we did was to look at the poor predictions of the February 2018 SSW, which led to the extreme cold wave known as the Beast from the East. And what we found was that there were poor predictions of a specific sort of breaking wave in the Northeast Atlantic, which we call the Scandinavia-Greenland dipole, which enhanced the amount of wave activity that went up into the stratosphere and disrupted the wobbly spinning top. And then we built on this work by finding that current subseasonal forecast models struggle to correctly represent and predict this pattern more generally, not just in 2018, which likely precludes accurate subseasonal predictions of stratospheric variability. And so improvement should be made in modeling this pattern. Then, to consider the impact of the stratosphere on the weather below it, we went and looked at North America, where the influence of the stratospheric state is underexplored. And we did this by considering large-scale recurrent weather patterns called regimes and how their likelihood changes depending on the strength of the polar vortex. What we found was significant differences. So we found that the Arctic high was up to 7 times more likely when the vortex was weak versus strong, that the opposite was true to a lesser extent, but for a strong vortex for the Arctic low and Pacific trough. And then we found that in the Alaskan ridge regime, it was actually equally likely regardless of the strength of the polar vortex, but was particularly important for severe North American cold waves. And in some recent work, we've also explored the impact of an accurate stratospheric forecast on the accuracy of the regime forecasts, or how they change, finding that it does make a significant improvement, but the stratosphere is only one piece of the predictability puzzle for getting accurate subseasonal regime forecasts over North America. And so taken together, these results improve our understanding of subseasonal stratosphere-troposphere coupling and also highlight the key modeling challenges that we face.